Hey, hello everyone. Welcome back to my channel. Today we are going to be talking about lapse rate. Now, lapse rate means rate of change. And when we apply that to the field of meteorology, it refers to the rate of change in temperature as altitude changes. Now, there are two general types of lapse rate. We have environmental lapse rate and adiabatic lapse rate. Environmental lapse rate is a decrease in temperature as height levels in still air or the surrounding air, the environmental air, increases. Adiabatic lapse rate. Adiabatic means internal change. So adiabatic lapse rate is a decrease in temperature in a parcel of air as it rises or even as it sinks. Well, when it sinks, the temperature will not be decreasing, but it will actually be increasing. So let's talk first about the environmental lapse rate. In still air that is not moving, the general atmosphere, the general troposphere, what we will find is that temperature will decrease at a rate of 6.5 degrees Celsius with every 1,000 meter increase in elevation. And so we refer to this as the environmental lapse rate. As we can see in the diagram, at surface level, the temperature is 26 degrees Celsius. At 1,000 meters, the temperature is going to decrease by 6.5, and that is why it is 19.5 degrees Celsius. At 2,000 meters, temperature is going to decrease by another 6.5 degrees Celsius, and this is why it is 13 degrees Celsius at 2,000 meters. At 3,000 meters, temperature decreases by another 6.5 degrees, and so it becomes 6.5 degrees. And so I would like to ask you if we should go to another height level at about 4,000 meters, what would the temperature be at that point? All right, think about it and leave me your answers in the comment section. Now we move on to adiabatic lapse rate. Adiabatic lapse rate, as I said before, has to do with not the general atmosphere, but a rising parcel of air rising as a result of convection. So as air parcel rises, it is going to encounter atmosphere which is less and less dense, right? Because most of the air is the mass of the air is concentrated in the close to the surface. So the further up you go, the thinner it gets. Now this has an impact on the air parcel. What that will mean is that as the air parcel moves upwards, there will be less and less pressure pressing down on it. This is therefore going to allow the air parcel to be able to expand, as we can see in the diagram. So notice as the air parcel increase from ground level to 1,000 meters, it expands. As it rises some more to about 2,000 meters, it expands even further. Now, this expansion of the air, which is as a result of the decrease in pressure, is going to in turn have an impact on the temperature of the air parcel. So as the air expands, it is going to use up energy for this expansion, and therefore the temperature of the air parcel is going to decrease. Now, it's very important that you understand the difference between the way that the air parcel is decreasing, the temperature of the air parcel is decreasing with height, how that is different from the way the temperature of the general atmosphere is decreasing with height. In the case of the general atmosphere, what happens, two main things will cause temperature to decrease with height. It's because the sun is going to heat the surface, and the surface will in turn heat the atmosphere. So let me restate that. The atmosphere gets its temperature from the surface. All right. And therefore, the further you go away from the surface, the colder it will get. All right. So that's one factor. Another factor that I mentioned before is that the further up you go, the more, the less dense the air becomes, or the thinner the air becomes. And what happens is that because heat is being transferred by conduction, the thinner the atmosphere gets, the more difficult it is for heat to be transmitted from one level to the other. All right, so those are the two main reasons why it gets cooler and cooler in still air with height. In the case of the rising parcel of air, the reason the temperature is decreasing is because as the air rises, the pressure it is encountering will decrease. That gives it the room and the ability to expand. When it expands, it uses up temperature. And as it uses up its temperature for expansion, the temperature of the air parcel is going to decrease. All right. Now, it's very important to note that we're talking about the air parcel and we're talking about the surrounding air. It's as if the air parcel is somehow insulated. What I mean by that is that there is no exchange of heat between the air parcel and the surrounding air. So any changes taking place within the air parcel will not be influenced by the temperature of the surrounding air and vice versa. So this is a parcel of air at 0 degrees. Notice it is smaller and the temperature is 30 degrees Celsius. When it reaches to 1,000 meters, it expands But not only does it expand, the temperature decreases. So it's now 20 degrees Celsius. When the air rises further until it reaches 2,000 meters, it expands even more and more energy is used up. So the temperature decreases even further to the point where now it is 10 degrees Celsius. Now it's important to know that the changes in the temperature of air parcel takes place in both directions, both when air is rising as well as when air is sinking. So as air rises, it expands and temperature decreases. When air is sinking, it is going to contract because it is encountering higher and higher pressure on it. So it is going to contract, and when it contracts, it is going to warm up. So sinking air tends to warm as it sinks. Now, the rate of change in a rising or sinking air parcel will depend on whether that air parcel is saturated or unsaturated. We usually refer to unsaturated air as dry air and saturated air as wet air. And when we talk about saturated, we mean saturated with moisture, with water vapor. So in the case of unsaturated or dry air, we are talking about air that has not yet reached its dew point temperature. And because it has not yet reached its dew point temperature, condensation has not occurred as yet, right? So dew point is where the air is holding all the water vapor that it can hold at a particular temperature. And therefore, after that, we can expect that the air parcel, under the right condition, the water vapor under the right condition will change from a gaseous state to a liquid state. So as the diagram shows, the water vapor in the air parcel contains latent heat. Now, that latent heat was obtained during the process of evaporation, which is opposite to condensation. So evaporation is a cooling process. Evaporation cools the surface where the evaporation is taking place, and that is because the air is absorbing or should I say the water itself is absorbing the heat as it changes from a liquid to a gaseous state. The latent heat is used to change the state, but it does not change the temperature. Unsaturated air, as we refer to it as dry air, decreases at a rate of 9.8 degrees for every 1,000 meters. Or we could say, in most cases, it is rounded off to 10 degrees for every 1,000 meters. So if we write it in terms of every 100 meter, we would say that the temperature is decreasing at a rate of 1 degree Celsius for every 100 meters. All right, and this we're talking about, this type of adiabatic lapse rate we're talking about is referred to as the dry adiabatic lapse rate, or the DALR. Now, what about saturated air? Saturated air is air which has reached its dew point temperature, so condensation has occurred. Condensation, as I mentioned before, is the opposite of evaporation. And so it involves water vapor changing from a gaseous state to a liquid state. Now, what happens during the process of condensation so that the water vapor changes to liquid? The water vapor will need to lose some of its energy in order to change from a gaseous state to a liquid state. It does this by releasing some of this energy, and it releases this energy by converting some of it to sensible heat. Sensible heat now will involve changes in the temperature. Once the energy has been lost, then the water vapor is able to change to a liquid state. That sensible heat is released in the air parcel, and therefore it causes the temperature of the air parcel to increase. The rate at which the saturated air cools depends on the amount of heat which is lost during condensation, which in turn depends on the temperature of the air. Let me explain. So, cold air has a lower moisture holding capacity, so it holds less water vapor. Because cold air holds less water vapor, less heat is going to be available within the water vapor, and therefore less heat is going to be released in the air parcel during the process of condensation. Thus, the temperature of the air parcel does not increase significantly. Hence, the air will decrease at a rate of 9 degrees Celsius for every 1,000 meters. All right, so let me reiterate. Cold air does not have a lot of water vapor. Remember, it is the water vapor from which the heat is going to be released into the air parcel during condensation. So because there is not a lot of water vapor, a lot of heat is not going to be released. And therefore, it is not going to, when condensation takes place, the temperature of the air parcel is not going to warm up in any significant way. It will warm up, but it will not warm up a lot. So the rate of decrease in temperature is not going to be as much as the dry adiabatic lapse rate, which is 9.8 degrees Celsius per 1,000 meters. In this case, it is now 9 degrees Celsius for every 1,000 meters. But what would be the case if the air parcel had a warmer temperature? If the air parcel had a warmer temperature, it means that it would be holding more water vapor. And since it is holding more water vapor, then more heat, more energy is now going to be released into the air parcel. And so the temperature of the air parcel is now going to increase significantly. As such, after condensation has taken place and the air parcel heats up, then the rate of change of temperature with height, the rate at which the air parcel will be decreasing in temperature with height will be 4 degrees Celsius per 1,000 meters. Notice the difference. So for cold air, it would be about 9 degrees Celsius. I said about because the temperature will vary with the air parcel. So for cold air, it will be about 9 degrees Celsius for every 1,000 meters. But for warm air, it is going to be about 4 degrees Celsius for every 1,000 meters. And again, let me reiterate, the reason that this is the case is because warm air holds more water vapor, and the more water vapor it holds, the more heat or the more energy is going to be released from the water vapor into the air parcel, causing it to warm up. Because it gets warm, then it is going to cool more slowly. All right, let me take you back to the diagram so that you can see. So this is the general air, or the surrounding air, or the environmental air. It is this air in which environmental lapse rate takes place. This now is the rising parcel of air. When condensation takes place, the water vapor, which is one of the gases within the air parcel, among many other gases, the water vapor, in order for it to change from a gaseous state to a liquid state, is going to lose or release some of its energy. It's going to release that energy into the air parcel so that the air parcel will heat up or will warm up. And when the water vapor loses that heat, then the water can now change from the gaseous state to a liquid state. So this type of adiabatic lapse rate that occurs in saturated air is referred to as a saturated adiabatic lapse rate, or the SALR. What is the significance of lapse rate though? Lapse rate is significant because it indicates whether air will be rising or sinking, which will lead us into another topic that I will not go into in this video, but I will be sure to do another video that will go into the whole thing of air rising and stability. All right, so rising air is associated with stable weather conditions, while sinking air is associated with unstable weather conditions. All right, now let's do a little bit of map work. Yes, map work, even though we're talking about the atmosphere, this is not even a synoptic chart. This is a topographic map, and what you're looking at are contour lines, as you can see. The different height levels in meters. So if we have air parcels rising, and if at the church an air parcel has a temperature of 25 degrees Celsius, when it rises to the height at which the school is located, what will the temperature be? It will certainly not be 25. As it rises, remember, the temperature is going to be decreasing. So let's check it together. If when the air parcel reaches to the level of the church, which is 100 meters, it is 25 degrees Celsius, then it means that when it reaches 200 meters, and it is going to be, and we're looking at it in terms of the dry adiabatic lapse rate. So remember, the dry adiabatic lapse rate is going to be changing or decreasing by 1 degree Celsius for every 100 meters. So if it is 25 at 100 meters, at 200 meters, it's going to be 25 minus 1 degree, which will be 24 degrees. At 300 meters, and it will lose 1 degree more in terms of its temperature, and therefore it will be 23 degrees. When it reaches the height at which the school is located, which is 400 meters, it is going to lose another 1 degree, and therefore it will be 22 degrees Celsius. All right, so this is where we stop. You can leave your comments, and don't forget to like, to share, and to subscribe. Thank you for watching.